right, so we got about an hour for the lesson, a little bit less, and then we'll get ready for the competition when we're done with the lesson. So I started hitting recording now. So we're going to go over our objectives. It's actually not a lot. It's just that one of the objectives has many parts. These are all reactions. So every single one of these objectives is reactions of acyl chlorides. What's an acyl chloride again? That's one of those new functional groups we were taught that we needed to learn. Acyl chlorides are this. So today we're looking at reactions of acyl chlorides that are actually in structure very similar to carboxylic acids, extremely similar to carboxylic acids. They're actually even a little bit more reactive than carboxylic acids, which is the primary reason why a practicing chemist would make an acyl chloride, is because it is extremely reactive and it'll do all the things you want it to do very easily. So that's one of the reasons why they're asking you to learn about acyl chlorides, because it's a strategy that you can make these and then they're super reactive. All right, so you're also going to get the second mechanism today. How many mechanisms did I tell you there were in this unit? 2. So today's the last one. There's only 2. So you will have seen both of them after today's lesson. And this one's not too crazy either. I'm just telling you this is the one that is less likely to show up, but it has a non-zero chance to show up on the Cambridge exam. And explain the relative ease of hydrolysis of acyl chlorides, alkyl chlorides, and halogenurides. So those are our objectives today. Mostly we're going to be on reactions, which is why we're doing the team challenge, is to help you practice the reactions. All right, so acyl chlorides. I mentioned they're very similar in structure to carboxylic acids, extremely similar. And so carboxylic acids, we use them in synthesis, and they're cheap. So you can get ethanoic acid. I used it in the lab yesterday for ASChem. 3.8 liter bottle of vinegar is like, even with inflation, $3 at Aldi. So it's not that expensive. Carboxylic acids, we can use them to make many compounds. They are actually not the most reactive. They can do acid-base reactions, but they can't do a lot of other reactions. So most chemists, and this is what I was saying, will turn them into acyl chlorides first. And then from the acyl chloride, you could do a lot. You could do any of the reactions with benzene that we already saw, acylations, like you can put them on benzene rings to make some changes. And most medicines have benzene rings in them. And so most reactions of anybody who's trying to make a medicine, any pharmacist, would be a reaction that potentially is involving an acyl chloride. And so one of the key things here is to recognize that acyl chlorides are more reactive than carboxylic acids, which is why someone would start with a carboxylic acid and change it to an acyl chloride first. So carboxylic acid's cheap, easy to secure. You change it to an acyl chloride, it becomes more reactive. And so the first set of reactions we're going to look at is how to turn a carboxylic acid into an acyl chloride. And they're going to be reactions you might recognize. You might, because we did them back in ASChem. And so on the next slide, you're going to see the first set of reactions. And you should write all of them down on flashcards. You may recognize these reagents: PCl5, PCl3, SOCl2. Every single one of them, back in ASChem, we used all of these to go from OH to Cl on a compound. So in AChem, we're going to use these same reagents to go from COOH to COCl. The same swap is happening. This is how you get the OH group off and the fluorine on. And so you should write all 3 of these down, where these are your reactants, these are your products. You may recall what I told you last year, or you may not. Generally speaking, you usually only need to give the major organic product, meaning this plus this makes that. You may be also asked as a 1-point question to give the byproducts as the full equation. So last year I would have said, if you're shooting for an A level, you're going to need to memorize the whole thing. If you're just shooting to pass the Cambridge exam, then you only need to know the major organic product. So after you're done writing the flashcards, I'll do a couple questions for the major organic product just to remind you how to do that. So I'm going to pause here. So then these reactions are actually reactions we looked at back in AS Chem. It was how we turned alcohols into halogen alkanes. And so now we're still getting rid of the OH group, but with the C double bond O. So the carboxylic acid OH will turn into chlorine. So this is how you turn carboxylic acid into acyl chlorides. So I'm pausing to give you some time to write them down. And we'll take a look at what the expectation is for major organic products. Pausing for a few minutes until people are done writing. We'll continue to take a look at some example reactions. PCl5 and SOCl2 have no special conditions, but if you chose PCl3, these would be required. So you could put the little triangle there. And remember I said that if you're trying to pass, you give the major organic compound. If you want an A level, you can go ahead and memorize the byproducts as well. Some of the byproducts are easy to remember, some of them are difficult to remember. This segment has to also be balanced. I think this has to be a 3. Giving a little bit more time, a couple more minutes, and then I'm gonna give you some practice examples so you can see what type of questions you have. By 8:10, I will be moving on, just so you have the time. Remember, any flashcards you don't finish here, you're finishing at home on your own. But I'm trying to build in time clocks. All right, one more minute. Substitution, nucleophilic substitution, because OH minus, Cl minus is called a nucleophilic substitution. It's a good question. Like, what type of reaction is it? It is a nucleophilic substitution because nucleophiles, these are both nucleophiles. Both the OH group minus, Cl minus, they're both nucleophiles. So you're swapping out one nucleophile for another. All right, it is 8:10, so we're going to take a look at some practice questions. I'm going to write these. It says write a balanced equation using the structural formula for the organic compound and state any conditions necessary to show the formation. It says formation of propanoyl chloride. So propanoyl chloride is what? Prop means 3. So this is an acyl chloride. Remember, this means acyl. We talked about naming them, I think, in the unit 5, but we didn't actually work with them. So if you see oil chloride, that means you have an acyl chloride. So we have propanoyl chloride that we're making, which means we're trying to make this. And they say we want to make it from a suitable carboxylic acid. So you have to figure out what carboxylic acid that is. What carboxylic acid would make this? How many carbons long would it need to be? It would need to be 3, right? So they're just asking you, oh, so this is going to be propanoic acid plus SOCl2, right? Because it says they gave you the reagent. So it says write a balanced equation, state any conditions necessary. We didn't need the conditions. And then if you want to practice byproducts, remember this is the major organic product. So that's what we're primarily typically looking for, is the major organic product. But if you wanted the byproducts, they would be SO2 and HCl. Methanoyl. I always think these names are funny. Methanoyl chloride from a suitable carboxylic acid and PCl3. So methanoyl means how many carbons? 1. So literally just this. And so what carboxylic acid would that come from? Methanoic acid, which means just the same amount of carbons, but a carboxylic acid. And then we're putting it together with PCl3. Is there a special condition for PCl3? Look back at the last page because I did write it, and you're supposed to write it on your flashcards. If you have PCl3, you're supposed to know that it is heat. So how do we incorporate heat? We just write a little triangle. And then your byproducts. This one is yucky. So this is the major organic. So that's the primary thing that I'll be looking for in any challenges that we do, is the major organic. But if you were asked for the other thing, what would it be? H3PO3. And it's said to balance. So now we have to balance it. That means we actually need, because there's 3 hydrogens here, you need a 3 here and a 3 there to balance it completely because of the 3 chlorines. So the 3 Cls have to match the 3 Cls there, and then the 3 hydrogens for the 3 hydrogens in the acid. That's why you have to put the 3s. And the final one, butanoyl chloride. What would be the carboxylic acid that would make butanoyl chloride? Right. So COCl. I need butanoic acid, CH3, CH2, CH2, COOH, plus what? They tell us PCl5. And if you want to go for the byproduct, it would be POCl3 and HCl. No special conditions. So those are the types of reactions that you get to make acyl chloride. So once again, an actual practicing chemist, usually in the study of making a medicine, would start with a carboxylic acid because they're cheap to secure, and then they would change the carboxylic acid to an acyl chloride. And then once you have an acyl chloride, you can do a lot of reactions with it, specifically with benzene. You can add them to benzene rings very easily. And so that's how we get things like ketones on benzene rings, is because of acyl chlorides. That's how we get there. Continue. All right, so once we have acyl chlorides, what do they do? That's what's going to come up next. And you can do a nucleophilic substitution. So you may want to write this a little bit larger. ROCl, where R stands for carbon, like carbons and beyond, right? So ROCl plus HZ will give you the following general reaction. So the general reaction is this. It's going to be one you recognize. Do you remember when you had condensation and you took out water? Yep. This is just like it, except instead of taking out water, you take out HCl for acyl chloride. So they react extremely similarly to carboxylic acid. You take this out in every situation. So this means that your general products are going to be, in this reaction, what? They tell you here that it's going to be ROZ, where Z has replaced Cl, and then HCl. So basically, in every situation with an acyl chloride, you're going to remove HCl. Z could be any of these things. So if we have water, what would Z be? If we had water, what would Z be? Remember, water is HNOH. So Z would be OH, right? What if it was an alcohol? What would Z be? Let's try that one. What would Z be here? The H is going to go, right? So this whole thing would be Z, right? So the hydrogen goes, and then anything else that's left is whatever your Z is. We're obviously gonna check this out, but these are some examples of some things you can do. And so HZ could be, and you may want to write this down as a note, the different things we're going to be looking at in reactions. HZ could be water, where we take the H off and replace the OH. It could be an alcohol, where we take the H off and replace whatever. And then it could be ammonia. What's ammonia?
But it's to be an acid, right?
It's you end up with an acid. HZ is not necessarily an acid itself, because remember, alcohols are not acidic. They're basic. It just has to have a hydrogen and then something else. And the hydrogen goes with the chlorine and makes HCl in every single situation. So it's just like a condensation. But instead of removing water, you remove HCl. And it's a nucleophilic substitution reaction. So the type of reaction would be nucleophilic substitution. We're getting the chlorine off and something else off. So this gives you tons of transformations. You can make a bunch of different functional groups with this. So it could be water, it could be alcohol, it could be ammonia. What's ammonia again? NH3. Or you could be adding an amine, which means you could be adding something from like this. Anything from here, you're going to be able to recognize how it reacts as we look through examples. Can R be what? The R could be any carbon chain. This has to be, R stands for carbons, with just unspecified amount, 1 to hundreds. Like it could, they're not going to give you hundreds on the Cambridge exam, but could they give you a 10 carbon long chain? Sure. Like they could give you a ring, they could give you a ring with it on it, like a cyclohexane R. So let's take a look before we get to additional topics. Let's take a look on how to do this reaction. So I believe you can head to the back of your, if you need extra space, you can head to the back of your paper because there's extra space there, where I have the team distribution points, which I'll be talking about in a little bit. But I think we should do some general practice reactions just so you can get the hang of what this looks like. So let's take a look at a few reactions. They were listed. Base. All of these are bases. So base. The condition is it's in basic solution. Condition base. Okay, so let's take a look at a couple of reactions. Let's start with this one. I'm just going to write base. What would the product be? Predict the major organic products and also predict the byproduct because it's easy to get both. What would you do? What's the method of this reaction? The nucleophilic substitution, what's getting out, what's getting out?
It's
And H2 is going.
And H2 is going in because H is going with Cl, right? So what you have to recognize is H is going with Cl every time, and then the nitrogen here is going to link in. So this is going to become +1. H HCl. And so it does bounce every time. And it's 1-to-1. What did you just make there? What is this? You can use this to make a amide. So if you needed to make an amide, you would introduce an amine to an acyl chloride. Let's try another one. What if I had, and we'll do it on this side this time. Plus, what would you get? I just want you to get the hang of the reaction types. So that's why I'm giving some practice. We remove the H with what? Remember, you're always removing the H with the Cl. The H next to the electronegative atom, always with the Cl. And then what links in? Oh. I guess. I could just write the whole thing in skeletal, but I didn't. Just change that to skeletal. Right? What is that? That's an ester. So I can make an S. That's not. Again. That's an ester. So I can make an ester this way. So far, are you following me? So acyl chlorides can be turned into amides. Acyl chlorides can be turned into esters. Let's see what else they could be turned into. Let's do random acyl chloride plus water. Yep. Base. So what do we do here? The H goes with the Cl, and we merge the rest together. So you're going to get a carboxylic acid plus HCl every single time. So your byproduct for all these acyl chloride reactions is the hydrochloric acid every single time. So this is actually really cool because you can use this to make an amide, you can use it to make an ester, you can use it to make a carboxylic acid, which is funny because we use carboxylic acid to make acyl chlorides. So this is if you want to go back to a carboxylic acid for whatever purpose later on. So you may want to change something to an acyl chloride to make it more reactive, and then later on change it back to a carboxylic acid for whatever your final product is. And so this is a method to get there. So I would not write down every single individual variation on a flashcard. I would just write down the general. The general reaction type, meaning this to this. So if you haven't written a flashcard for this yet, I advise writing a flashcard for the general reaction only for acyl chloride. I mean, you can write down all the individual variants if you want, but they all fit the same type. So if you understand the type, it's going to be less to memorize. So I'm giving you a little bit of time to do that, and then we're going to move on to hydrolysis. Yep. This is actually a hydrolysis reaction, also a hydrolysis reaction if it's water. Right? Okay. So we're going to talk about hydrolysis next. And so if you're ready, we'll move on. Hydrolysis of acyl chloride. So if we are specifically doing this reaction instead with, if we are doing this reaction with water, we call it hydrolysis. Because you're putting in water to break apart a molecule, but you're really just replacing the chlorine with the OH. But it can be called hydrolysis. And so there is a relative, so this is the same reaction we already saw in the last slide. It's just if it's with water, we can call it hydrolysis. And so they tell us here that the ease of hydrolysis, which means most reactive to least reactive, is in this order. Meaning that acyl chlorides will be the most reactive, will undergo this reaction very easily. Chloralkanes will be a lot less reactive than that. And aryl chlorides actually will be extremely unreactive. And one of the standards today was for us to be able to explain why. So let's draw out each of them. What does the acyl chloride look like? COCl. That's what makes an acyl chloride, and then you have whatever else. What does a chloralkane look like? Chloroalkane. So they're saying this is more than chloroalkane. Alkane is what? Just a bunch of carbons and hydrogens, right? So it'd just be something like R and then CH2Cl. That's a chloroalkane. And then an aryl chloride, what is air in the front mean? AR. Means benzene. Air, arene, aromatic. Air in the front means benzene. So if I see AR in the front of a name, this tells me I have benzene. So an aryl chloride would be benzene with a chlorine. And they tell us that the ease of reactivity, so this is going to happen easiest with water, and this is going to happen, it's not really going to happen with water at all. And what Cambridge is asking for us to explain is why. So why would it be this order? And the answer will lie the same place it lies in almost every explanation for this unit. Electron donating groups versus electron withdrawing groups. So anytime we're asked to explain an order of what's more reactive, what's less reactive, what's more acidic, what's less acidic, we have to talk about electron donating groups versus electron withdrawing groups, and if that strengthens or weakens the here it would be the COCl bond, the CCl bond right there. If it strengthens or weakens that bond. So those are the points we have to hit every single time. We hit them with phenol, I think last class. And so now we're going to talk about it again, but now with acyl chlorides. So why is this the easiest to react? What about it makes it the easiest to react? What is that oxygen there? Withdrawing or donating? It's withdrawing. So this is a very electronegative atom. So that makes it withdrawn. And the understanding of that is if it's withdrawing, it means the electron cloud is pulling away from that CCl bond. So in an acyl chloride,
And COH doesn't do that?
we're not doing that comparison right now, but we did that last class and it does do that. It does. Yes, COH does do that. It is an electron withdrawing group, and that makes carboxylic acids more reactive than what they would be compared to, which is phenols or alcohols. But here, this actually, and that's interesting, the COCl is more reactive than the carboxylic acid because the CCl bond is a weaker bond to start with. Like this has a lower bond energy than the COH bond. That's why. Like because this is a smaller bond energy to start with, if I'm pulling electrons away from it, then the bond weakens even more, making it even less energy to overcome. So it's going to react very fast. Does that kind of make sense? Okay, so in an acyl chloride, the electron withdrawing nature of OH, or the C double bond O, pulls electrons away, weakening the BCl bond, making it easier to break. That's what we're about to go over. So I discussed the first one, right? We have to talk about each one. So what's going on with a chloralkane? Why would that be less reactive? Does it have an electron withdrawing group or is it an electron donating group? So this right here, because it's just carbons, right? Carbons are not very electronegative. They're not withdrawing electrons away. They're actually putting electron density in to that bond. So because it's an electron donating group, we actually write it like that, where the electrons are being donated in to that bond. So the way I would explain it, in an alkyl chloride, because the R group is electron donating, the CCl bond is strengthened. Which makes it harder to break and less reactive. And less reactive. Remember, there's a whole entire standard where we have to give this explanation, like what's happening here. So that's why I'm pausing to go over that. And then we haven't discussed the benzene. I'm going to pause to give you time to finish writing about the alkane, and then what in the world's going on with the benzene. Why is this the least reactive? Does anybody have any idea?
What?
The chlorine itself is actually an electron donating group, and its electrons get donated into the ring, which strengthens the ring, which means that this actually is extremely unreactive. So for the last one, the aryl chloride, in the aryl chloride, chlorine's electrons actually get delocalized into the ring because the chlorine electrons get delocalized into the ring, meaning they become part of the pi bonding system. And because if they're all part of that system, it's going to make it less reactive because it's stable as is. So it strengthens that bond. Gets delocalized into the benzene ring. Making it unreactive. And that's actually one of the reasons why if you don't have the catalyst for the electrophile in the other type of reaction, if you don't have the catalyst, is it going to happen? Not, right? Why did it disappear? Where did it go? My whole explanation. How did that even? Okay. Hopefully you were just on the last part. I can re-explain that. So for the aryl chloride, what was the reasoning again?
I sent that here.
Yeah, that's what I'm going to restate because it just disappeared and I don't know how that happened. So the idea is that with the aryl chloride, chlorine is an electron donating group. Donates its electrons into the ring, strengthening the pi bond system. I'm saying this a little bit differently. And because this is strengthened, this is extremely unreactive because it's stable as is, making the molecule stable and unreactive. So this was the acyl chloride explanation. The idea is because this is an electron donating group, it actually strengthens the whole ring. And so it makes the chlorine very unreactive, and therefore you have to have the catalyst for any of those other reactions because it's so unreactive. So the relative ease of hydrolysis would be acyl chlorides, easy. Chloralkanes, not really gonna happen. Aryl chlorides, you put that with water, that ain't doing anything. Like, it's not gonna react with water. Does that kind of make sense? That's the order. So why would we choose acyl chlorides? Because they're super reactive. They're super reactive because of the electron withdrawing group weakens the bond and the reaction's gonna happen. So you can do any of these reactions that I had already described. We have a couple more things to cover. The last big thing I'd say we have to cover is the mechanism. So we have a mechanism today. Oh, you're so excited. And this is called the addition elimination mechanism, because first you add and then you eliminate. Does anybody remember what elimination is? Elimination means make a double bond. So because they call it the addition elimination mechanism, the one that we're going to be looking at for this specific reaction, that tells us the order of what happens. We're adding something first, and then we're eliminating, meaning making a double bond. So that's going to give you the order that you see here in this reaction. As usual with mechanisms, I have one pre-printed for you at the beginning, so you have like where everything's supposed to be, and then we're going to make one from scratch, so you can see the process as it occurs. So the first step with an acyl chloride and hydrolysis is 2 electrons from the water go to the positive charge carbocation, the dipole with the positive charge. Remember, electrons are negative and they're always going to be attracted to positive charges. So this water actually links in and makes a bond with the carbon. But carbon cannot have 5 bonds. So one of the bonds has to break. Which is the easiest bond to break out of the existing bonds? It's always the pi bond. So this bond will break. So when this goes in, this bond breaks, those 2 electrons go up to oxygen. But this doesn't stay very long. So this is the addition, and then this right here is the elimination, which is these 2 electrons go back, and one of these 2 groups get kicked out, either the water or the chlorine. The bond that's weaker gets kicked out. And I think I just told you, the CCl bond is weaker than the CO bond. So the CCl, the chlorine will get kicked out. That's what gets kicked out. And so you end up with this. But that's not normal. That's not what it ends up with. So you get the Cl minus from before, picks up a hydrogen, and you get carboxylic acid. And that's your answer. We're going to create this from scratch, obviously. This mechanism will be worth 2 or 3 marks. But it also, it's its own reaction. It's different from an SN1 or SN2, as it says down here. It's called addition elimination because first you're adding something and then you're restoring the double bond, which we call elimination. We're going to take a look at it from scratch. So we're going to skip this question for now. We'll see if we come back to it, but I want to do the mechanism. So write the mechanism of the hydrolysis of propanoyl chloride with water. So what's propanoyl chloride? How many carbons? CH3, CH2, CO, Cl. And then it's going to be plus water, which it would probably help if you wrote it out the way that it exists in the blue structure, because that'll help you to figure out what's going on. For any mechanism, what should we write first? This actually is true for all mechanisms except free radical substitution. What should we write first? Dipoles. Perfect. So we can assume that Mark 1 is most likely going to be our, I mean, it depends on whatever grading governing body you have, like that year, but usually Mark 1 is going to be your dipoles. So where are my dipoles? On my organic molecule, because that's got to be where you start. Carbon positive and oxygen negative. That helps you figure out what happens in the first step. The electrons on oxygen are going to be attracted to which thing? The negative oxygen or the positive carbon? The positive carbon. So the next thing you do is you take either pair of electrons from water and you make a curly arrow. There. So far, so good? Can that carbon have 5 bonds? Because remember, these 2 electrons make a covalent bond. Can that carbon have 5 bonds? If you write it with 5 bonds, I said in my AS class, what I want to buy over the summer is like a stamp that says the octet police. You broke the octet rule, like with like a little cap.
Somebody had extra.
You broke the octet rule. And they went one step farther. They were like, we should write tape like how you have a hard corner, and be like, that's the octet jail. And go sit in the octet jail. You broke the octet rule. I think it's a good idea. I want to get like an octet police sticker for like whenever on a test I see that somebody wrote carbon with 5 bonds, and be like, octet police. You broke the law. Get in jail. Anyways. So the idea is that you have to break one of these bonds. Which one? Which is the easiest bond to break out of these that are existing right now? The pi bond. So then that goes there to make 2 electrons. And so now you have 4 bonds, which is okay. So we draw our product from the first step. So mark 2 is your curly arrows, right? In step 1. That's the most amount of marks you could get for step 1 is 2. 1 for the dipoles and 1 for the 2 curly arrows that you need. Now our product. Usually there's a mark for our intermediate. Mark 3 is the intermediate. What's our intermediate? CH3, CH2, C, single bond O, single bond Cl, and then like olive water, right? Like that. Wait, that's an interesting thing. Don't look normal. It ain't normal. Oxygen actually has a positive charge here. Right? We learned about formal charge. It only has existing 5 of its 6 like normal valence electrons. That's strange. That's really strange. So that cannot be our final product. So what do we do now? So the addition, we did the addition. Now we do the elimina. If you remember the name of it, you're going to remember the steps. Addition, we added. The next step is elimination. So elimination means we get the double bond back. So that means we're going to put these 2 electrons back here. But carbon can't have 5 bonds. So which of these 2 break? Because the chlorine. Because it's the one that's the more reactive, it's the lower bond energy, it's going to be the one that breaks. So chlorine gets out. Like, bye. Okay, so we get this. CH3, CH2, COO. Okay, right? That's where we're at right now. This is where we're at. This was step 1. This is step 2. But that ain't no carboxylic acid. We have to grab that hydrogen back, right? So to make it more stable, the final step is to do what? Take away that hydrogen. And what's going to take away that hydrogen? What's there that can take away that hydrogen? We just put chlorine off to the side, right? We got Cl minus. So can't Cl minus be like, hey, join me? Because isn't one of your products HCl? No. You're just describing how that happens. So you get this. There's our other team member. CH3, CH2, COOH. And the other product is? HCl. And so this is the proof of the reaction I just taught you today. This is how it happens. It is the mechanism. Hi. Go on in. We're going to start in a little while. How's our brains? Fried. We literally just learned like one thing.
Well, it must be like suffering from microscope.
Oh, okay. That makes more sense.
Worse.
The reactions in AS are harder because most of the reactions in A can be grouped together into a single type. And so if you just remember the type you're looking at, you're going to be fine. If you can remember the type that you're looking at.
Which is my name.
All right. So, let's have you try one yourself. Your turn. And then this will be the last slide for today, and the rest we'll put into next lesson because we need to get ready for your tournament. So the next slide will be the last slide for today. So I've taught you the reactions of acyl chlorides, and I've taught you how to make them, and I've taught you the addition elimination mechanism. So that being said, last slide for the day. You're gonna write out a mechanism of your own. You've got about 3 minutes to do this. Try it yourself. And then our challenge will start at 8:55. So write the mechanism first, have me check it. The next slide, right there. You try this one. See if you can try this one. Have me check it, and then as soon as you're done with the mechanism, you're gonna get in your teams. And at 8:55, I'll start loading everything up. So. Try this one yourself.
I know.
See if you can follow the steps. Do you need me to go back to the other slide to finish? You need me to go back?
Oh.
We're good. You need me to go back here?
You know what's funny? You look tired. Oh
Yes,
my God. You better not. Did you study?
He didn't.
Are you like crying? Hello?
Yes.
Are you crying? Why are you crying? Are you okay?
When you are done with the mechanisms, have me check off on it, and then
Okay.
one person per team is getting a computer.
You either been studying? I had dual real bitch. I had dual. This.
You're the helper.
I'm the helper? No. I was like, look, I remember this, and I was like, oh, I remember this, and then I got to a point, and I was like, oh, I don't remember this. Like,
Okay.
I was gonna send you that one. And then like, I'm like,
Is this that?
I'm like really hoping everyone's like,
So
so am I.
the hydrogen's coming from the
Like, ingenious.
I really good video. It's very small.
Yes.
It's NH2, right?
No.
No.
That's ammonia,
No, I mean, it's NH2.
right? So ethylamine is
Wait, why am I cooking you? Oh, wait, this is on the test. Competition.
Okay.
right. So remember, this is the hydrogen that's going to form.
Yeah.
So
No.
you have to write your diagram.
You know what's more
Well, between means and Alright, see if you can try the next one.
Those are the worst.
Once you're done with the mechanism, have me check it off.
Oh, okay, okay. Let me write.
So far. So how would you do if it was amine and not water? You still have to follow the same strategy. Addition, elimination.
It's fine, right? So it has 3 bonds, so then it's 2. So that's one. Yes, I have a big problem with my teammates.
You bought it down. Yeah, I guess. No. It is.
Oh, but it's a mechanism. Oh, no. Oh, no. Wait.
This carbon has 5 bonds. That's like a stop. No.
Wait, I saw this, right?
How bad is
What?
You gotta go on like a roller coaster with me.
Okay, I get to read a roller coaster. That's what I missed about the.
Oh, that's hard. Okay.
Is that it?
Why did the other
Is that it? Are we like super geniuses right now? I don't think so.
No, you're not. Oh. I
know. Yeah,
Oh,
that's
Everybody laughed at that.
You're right. I put a spawn to the
What makes it go? What makes it go?
when I get to
So I fixed it.
That's only 2.6.
What? You're a degenerate.
That's like an 80%. Is this?
You give it a lot of color.
my
This is the way that they read it.
Evil.
And then we go to the
And
next
the
step.
difference.
Oh, and then we gotta.
Oh, wait, no.
Yeah, it's go here. And then the next step.
Do you know what a degenerate is?
Who's there
You understand?
Where did I make my first mistake? I know it's not right. Where did I make
Wait
my
a
first
minute.
mistake?
Last.
Oh, the part is we forgot to.
Something ain't right.
Oh, wait, so we have.
Okay, David.
Yeah.
Let me tell you.
And then we take.
This, that, and this.
Oh, did you know I won against him?
Yeah, you won't mind look.
And then
No,
it's.
that was strategy. My brain, I'm not gonna lie, my brain was on it.
Okay.
It's good. Let me give you the perfect stamp.
It was kind of my fault because I switched out some things I haven't because I had already seen that card.
But it could be on next week's, right?
Get out!
Is that it?
Let me check. Am I checking? All right, so we got a perfect stamp going on. Let's see. We forgot a curly arrow to go in there, right?
Oh, I was doing it right the first time, but I felt
Let's see it.
We got this.
You're missing the carbon chain here. Like you've got the, you're
You
missing
guys
the
study.
C2CH3
You're like.
because there's C2CH3 connected.
Yeah. Would the CL connect to the CA?
CL takes the hydrogen. So the chlorine's by itself, and then it takes the hydrogen. But at the bottom, you should have the CH2CH3.
I got some vibes.
No, it's part of the final product because it's not disconnecting
It's gonna add to
eventually. It's gonna add, like it's part of this and the CH2CH3 is all the stuff that connects. That whole, what I'm saying is that has to be there. Like, because it's part of that whole thing, that's remember we talked about what Z was? That's what Z is. So Z has to be there. All right, let me check.
This is the base. I guess.
I understand it.
that you don't like it.
Good. Oh, great.
So the one breaks and then the.
I understand that.
You what? We need mechanisms right now.
I understand that.
Okay, so you've got about 3 minutes. At this time, you should be getting 1 device per group. One device per group. It's today.
I didn't feel like it was a good.
1 device per group. You must use your
I said
group
it.
name. You must use your group name in the cahoots.
What flavor is that?
Before we begin, and we'll finish these on Monday, but before we begin, here is the tournament points spread. Every group competition, first place getting 7, second place 5, third place 3, fourth place 1. When you have an individual quiz, which won't be yet, I'll let you know the class period before when the competition is an individual quiz. Then it's 80 to 103 points per person.
Yo, you're an actual.
Then 2 points.
I think it's literally gambling.
That's
One time we're going.
I'll let you know the class period before. Yes. Yes.
Manuela Córdoba, please come down.
She's not here. This is not this class. She's second period.
Thank you.
That lady is screaming.
Okay.
Ah.
So I'm gonna go ahead and look it up.
Using my.
This is the A-level Hunger Games. Can we have our notes out? No. Put your notes away.
No!
One to fight. Put your notes. Put your flash.
Put your notes away.
I'm putting it away.
Put it all the way away.
I'll let it.
Self-described best class ever.
Miss McMilk is a cheater.
We are the best
Is
class.
happening right there?
Yes, you can.
What? Say.
Oh,
All right. Put your flashcards away.
Wait.
Put your notes away. Use your team name in the Kahoot. This makes
Steph, wait, are you gonna do this?
Because you're the
But it does.
Look at him.
because you're the one who solved it.
Every question will be 30 seconds. Who was that?
I am always.
You're allowed a whiteboard and a whiteboard marker.
You know why?
Somebody got
No reason.
whiteboard,
You can
whiteboard.
have blank paper and pencil. I don't think my name is appropriate. That's why I
Get away. Just put these.
Okay, South Rock 73 needs to get out. We
I
need
have the
to-
markers. Get a whiteboard.
Oh, I told you.
Where is
That
the napkins?
1 per
In the
group
back.
to share. It's gonna be 30 seconds per question, so these gotta go away.
Oh, yeah. Right.
All right, David, put your stuff
I
away.
even know
I'm on it.
Team Movie Gumi is in. You should sit with your group members. 1 whiteboard per group. It's gonna be 30 seconds. You may not have very much time. You can also have scratch white paper and a pencil.
Hear me out. Hear me. We're gonna do the following.
I like it. I like the flowers.
One more group.
Again,
Okay.
You guys want to change
On the phones?
what we're doing is
Yeah.
one person has to put in the answer. But
Because
if you feel confident, you
You're so smart.
Just don't put space.
Alex and Seth. If you feel confident in the answer yourself, just grab the marker, write it down.
Oh, it's right there. Can you imagine?
Emphasize the
What's the other? Since we're 30 more seconds of questions, I'm assuming there's not any crazy questions about mechanism.
30 seconds per question.
And I don't think we're going to see this like no
gotta go.
Probably not.
Yeah.
right here is brain better.
No, the answer for them, chicken butter.
All right, we're starting in 30 seconds.
Put that down and I'll put it.
Get out, bro.
Get out of here, bro. Get out. I wouldn't want to do it.
I'm scared.
I should stop recording.
Gambling right